In this video, we're going to learn about ionization energy and how we can predict ionization energy using the periodic table. Throughout the course, we've talked about how an atom can lose electrons and take a negative charge. Well, in order for that to happen, you've got an electron that is close to a nucleus and happy about being close to a nucleus, and you've got to remove that electron. That requires energy. We call that the ionization energy. It's defined as the minimum energy required to remove an electron from the ground state of a gaseous atom or ion. So the fact that it's in the ground state, you've got an electron that is in its lowest possible energy level, and you're going to remove it. If you remove one electron from an atom, we call that the first ionization energy. If you then go and remove a second electron, we call that the second ionization energy, and so forth. So the higher the ionization energy, the more difficult it is to remove an electron. Each electron that you remove from an atom requires more energy. So what I mean by that, your first ionization energy, which in this table is listed here for several different elements, will always be lower than your second ionization energy. Take aluminum, for example. Aluminum has 3 valence electrons. There are 3 electrons in the outside energy level for aluminum. Removing the first one requires 578 kilojoules per mole. Removing that second one requires 1800 kilojoules per mole. Removing the third one requires 2700 kilojoules per mole. At that point, you have removed all of the valence electrons for aluminum. When you switch from valence electrons to inner shell electrons, you see a large jump in ionization energy. It's pretty common to remove valence electrons. It's pretty rare to remove inner shell electrons. We can use the periodic table to predict how ionization energy changes for different elements. When we do this, we tend to just use the first ionization energy. So the trend that we're about to look at is how first ionization energy changes as you go across the periodic table. It generally increases as you go from left to right, and it generally decreases as you go down. Recall in the previous video we talked about the size of the atom and how that changes across the periodic table. And we said that the largest atoms are down here in the lower left. Well, ionization energy is affected by that. Smaller atoms have higher ionization values. The smaller an atom is, the closer its electrons are to the nucleus. An electron close to the nucleus is going to be much harder to remove than an electron that is far away from the nucleus. So if you think about helium, helium has 2 electrons. They're both in the first energy level. It's really going to be difficult to remove one of those electrons. Whereas cesium's got 1, 2, 3, 4, 5, 6 energy levels. So its outer electrons are 6 levels of electrons away from the nucleus. These are going to be pretty easy to remove. They're not feeling the force of the nucleus nearly as much as helium is. So ionization values depend on the nuclear charge and the average distance of the electron from the nucleus. You can see that it increases as you go from left to right, and it decreases as you go down. This arrow represents the general trend for ionization energy. It's the highest in the top right of the periodic table. There are some exceptions to the ionization energy trend. One example would be right here where it's been raising and then all of a sudden it drops. Here are the reasons why you have those exceptions. It has to do with the valence electrons. So the trend is not followed when the next added valence electron enters a new sublevel. So for example here, all of these are in the D sublevel. This next electron, when you go from zinc to gallium, the next electron would go into a P sublevel. So you see a drop in ionization energy. Another time when you see an irregularity in this trend is when you add a valence electron, and that is the first electron to pair in an orbital. So, for example, nitrogen, all of these electrons are unpaired. There's just one in each orbital. But when you go from nitrogen to oxygen, that next electron pairs in an orbital. So you have one up, one down within that orbital. That causes a drop in ionization energy. So that's just two of the reasons why sometimes we see some irregularities within this trend. Just make sure you're familiar with the overall trend. So ionization energy is the energy required to remove an electron. So that's energy when an atom is losing an electron. The opposite of that is electron affinity. This is going to be the change in energy that happens when an atom gains an electron. Generally, when an atom gains an electron, it drops in energy. It's exothermic. So for most elements, this is going to be a negative value. Let's take a look at the general trend for electron affinity on the periodic table. As you go down a group, there's not very much change. As you go across a period, it tends to increase. However, there's some exceptions. The exceptions are right here between group 2 and 3A, and right here between group 5 and 6A. It has to do with the sublevels. When you go from here to here, you've filled up your S sublevel and started adding to your P sublevel. So your electron affinity value was raising, but then it dropped right there. And then it continues to raise again, and it drops after group 5A. At that point, your P sublevel is half full. For nitrogen, your P sublevel looks like this. Each orbital has one electron, but for oxygen, you've gone beyond that half full point. That causes a drop in the electron affinity. The last thing that I want to point out is that your noble gases tend to have positive values for electron affinity. These are more stable as atoms than they are if they gain an electron. So these are not ever going to gain an electron.